Hi, everybody. My name is Isao, and I'm a tutor with Medlearnity. Today, we'll be doing a biochem question. So please take a few moments to read the question to yourself and then think about what the right answer might be, and then we'll go over it together. So now that you've had a chance to read through the question, I'm going to read it out loud and highlight what I think is important to know from this question. So we have a 30-year-old man who's brought into the emergency department with slurred speech, unsteady gait, and significant CNS depression. So already there's a couple of different things that could be causing this, but we have a mental picture of what the patient looks like when they're brought into the ER. So he had just gone out drinking heavily with his friends until EMS was called to bring him into the hospital. So most likely the alcohol was the direct cause of his current symptoms. Finger stick glucose on admission is 53, it's quite low. pH is 7.2, it's also low. Sodium 123, chloride 97, and bicarb 7. BUN 22, creatinine 1.1. So levels of beta hydroxybutyrate and acetoacetate are elevated. So these are going to be ketone bodies. Acetone is the last one as well, but it's not as commonly measured. And then elevated levels of which of the following is responsible for the metabolic abnormalities seen in this patient? Okay, there's a whole bunch of issues going on here. So I think the easiest way to approach this question is simply to write down all the different abnormalities. So there's hypoglycemia. The finger stick on admission is 53. There is a low pH, so acidosis. And if you calculate anytime you're given the BMP in the context of an acidosis question, you should actually calculate the anion gap, because you want to know if it's an anion gap or a non-anion gap metabolic acidosis. And actually, if you calculate the one here, you will find that if you do 123 minus 97 minus 7, so 19 is our anion gap. And as you probably know, the mnemonic mud piles will give us a differential for some of the potential causes of a high anion gap metabolic acidosis. BUN 22, creatinine 1.1, so we can also calculate the BUN creatinine ratio, and if it's above 15 or above 20 is usually the right number to use, then we say there's a pre-renal azotemia. So maybe this patient's a little bit dehydrated as well, but it's not a central part of this question. The BUN elevation is not too high, but we can say that it is a little bit elevated. And then elevated ketone bodies. So we know that all of these are going to be caused by the patient's alcohol. And so I think it's important to talk a bit about ethanol metabolism for this question, because it'll help us understand why ethanol metabolism can lead to this whole host of metabolic issues. And in so doing, we'll arrive at the correct answer, because only one of these listed here will actually be directly responsible for all the above issues. So let's start off by going over ethanol metabolism. So ethanol, when it's ingested, it's converted into two things. The first thing it's converted into is something called acetaldehyde, and acetaldehyde is converted into acetate. Now, what's important to know is that the conversion from ethanol to acetaldehyde produces NADH from NAD+. And also the conversion of acetaldehyde to acetate produces NADH from NAD+. The reason this is important is that if you only ingest a small amount of ethanol, it'll increase your NADH levels, but not by that much, and your body can still continue its other metabolic pathways as normal, and there really isn't much of an issue. But this patient clearly has outdone himself, and he's ingested a large amount of ethanol to the point that we can pretty safely assume that this patient has a pretty elevated NADH to NAD plus ratio. So let's pause for a second. So NADH, you probably remember in the context of the glycolytic pathway, the TCA cycle, and the electron transport chain. NADH is produced from both glycolysis and the TCA cycle, and those are both shuttled to the electron transport chain where they drop off electrons to ultimately produce ATP. Now, the reason that this whole pathway can proceed is because there's a proper balance between your levels of NAD plus and NADH, such that if you have a lot of NAD plus around, it signals that you're going to want to produce more NADH so that those can ultimately be converted into ATP as they drop off their electrons. But when you have a lot of NADH around, what that's suggesting to the body is that you've converted all your NAD plus already. There's no need at this moment for more production of NADH, and it'll halt all these pathways that we've been talking about. So I think the next most helpful thing to do is to actually hone in on the TCA cycle itself. And to do that, I'm actually going to use the help an image that will, instead of drawing out all the intermediates that'll take up a lot of time, we have this whole pathway already here. And what I'm going to do with this is there are two key steps, or three key steps in the TCA cycle that I think you should really focus on for this question specifically. And I'll just say as a brief aside that I don't personally think it's that helpful to memorize every single intermediate. You'll never be asked what the enzyme aconitase does. That's just not a very useful question for step one. But I think the way to approach the TCA cycle is to know that, for example, malate is part of the citric acid cycle. Know which steps produce NADH, know which step produces FADH2, know which step produces GTP. These are the key steps, and those are going to be highly testable, but all these small minutiae are probably not worth your time. If it helps you to memorize it and helps you feel more confident, then that's great, but I think that there's already a lot to know for this exam. Picking and choosing the most important parts will be a better use of your time. But so back to this question now. The three steps that I wanted to focus on are the conversion of isocitrate to alpha-ketoglutarate, and this is done by the enzyme isocitrate dehydrogenase, and then alpha-ketoglutarate to succinyl-CoA by alpha-ketoglutarate dehydrogenase. And as you'll notice, they both produce NADH. And so back to the previous discussion, since this patient ingests a lot of alcohol and has significantly elevated the NADH to NAD plus ratio, NADH will actually inhibit these two steps. So this symbol here is for inhibition. And effectively, these are two of the rate limiting steps of this cycle, and they will, since NADH is inhibiting them, it'll slow down the citric acid cycle, and everything before it will back up. And the last pathway that actually produces NADH, or last step here, is the enzyme malate dehydrogenase that converts malate to oxaloacetate. So NADH also will inhibit this step. So what happens as a result is that everything back here will be backed up. And in the end, you get a very large elevation in acetyl-CoA. And that'll lead to a bunch of different consequences. So acetyl-CoA is a hub in the sense that beta oxidation ends up producing acetyl-CoA that can enter the citric acid cycle. Acetyl-CoA can be combined with oxaloacetate to make citrate, and eventually the oxaloacetate can actually go back and produce glucose through gluconeogenesis. So it's really a key molecule to know, and a lot of the consequences of an increase in acetyl-CoA will result. One thing to talk about is actually the production of ketone bodies. So ketone bodies are produced from acetyl-CoA. So let me write this all down. So ketone body synthesis starts with acetyl-CoA. produces acetoacetyl-CoA and a whole bunch of other intermediates that ends up producing beta-hydroxybutyrate, acetone, and acetoacetate, as mentioned here. So those will be elevated. I talked briefly about gluconeogenesis. Oxaloacetate can be converted into PEP phosphoenol pyruvate, which is one of the steps of glycolysis, and it'll basically reverse the steps of glycolysis and go back to form glucose. But in this context of this patient where we have an elevated NADH level, since this step is being inhibited, actually we have an arrow going this way, but these are actually reversible reactions. So we can draw this double arrow. And when you have an elevated NADH, it's going to drive the reaction in this direction. So oxaloacetate will preferentially be converted into malate, and it'll basically deplete your stores of oxaloacetate for gluconeogenesis. So ketone biosynthesis will increase, malate will increase, oxaloacetate will decrease, and the net result of that is decreased gluconeogenesis. And so if we look back at the patient's lab values, the finger stick was 53, so the patient's hypoglycemic, and that is because not only gluconeogenesis is being inhibited by drawing oxaloacetate away, but also if the patient didn't eat anything all night, they can quickly deplete their stores of glycogen, and so really the patient's left with no glucose lying around. So that'll be the cause of the low glucose levels. Another consequence of this whole pathway being backed up, and again, we're all tracing this back to this elevated NADH level, is that acetyl-CoA is the substrate for producing fatty acids. So ketone biosynthesis increases. Acetyl-CoA through the rate-limiting enzyme acetyl-CoA carboxylase will lead to fatty acid synthesis. So actually, if you were to measure the fatty acid levels in this patient, they would be elevated. Malonyl-CoA is actually the molecule that acetyl-CoA is converted into by acetyl-CoA carboxylase, and malonyl-CoA is a powerful inhibitor of beta oxidation. So not only is fatty acid synthesis increased, but fatty acid oxidation is inhibited. So fatty acid oxidation goes down, and those kind of go hand in hand, and that makes sense. And the last thing I wanted to mention is the anion gap metabolic acidosis, and this has two origins. So the first one is the ketone bodies that we already talked about. Ketosis is a common cause of an elevated anion gap, but the other one is an increase in lactic acidosis, or lactate. And to understand this, so if we look up here at pyruvate, this is the last substrate of the glycolytic pathway. And in the context of an elevated NADH level, where the body's going to naturally want to replenish the supply of NAD+, and the only way that can be done without the electron transport chain is to convert pyruvate to lactate. Let me change my color here. So pyruvate will be converted to lactate, and in this process, NAD+ is regenerated from NADH. So just to bring this all together, the patient has ingested a lot of alcohol. The ethanol is converted to acetaldehyde, and that's converted to acetate, and so we're increasing the levels of NADH and subsequently the ratio of NADH to NAD+. So this elevated NADH is responsible for a lot of different things. It inhibits these three important steps of the citric acid cycle. Since the citric acid cycle is blocked up, acetyl-CoA levels will increase. Acetyl-CoA will be a substrate for ketone body synthesis, for fatty acid synthesis, inhibition of fatty acid oxidation. Also, since this last step here is inhibited, oxaloacetate will be converted to malate instead of being shunted to gluconeogenesis. So gluconeogenesis is inhibited, so the patient will be hypoglycemic. And then also because of the ketone body elevation and the elevation of lactate that results from the desire of the body to regenerate NAD+, the lactate levels will go up. And these two together are responsible for the anion gap acidosis seen in this patient. So bringing it all together, I hope it's clear why the answer to this question is the NADH level. That's really responsible for everything that we've talked about. Just to go over the other answers here. So the lactate level is responsible for the anion gap acidosis, at least partially, but won't explain all the other metabolic issues here, like hypoglycemia, ketone bodies. Beta hydroxybutyrate is a ketone body, so that'll be responsible. That'll account for the elevated ketone levels and acidosis, but again, not the hypoglycemia. And then citrate is one of the intermediates in the TCA cycle, but it's really not a direct cause of any of the metabolic abnormalities in this question, so we can cross that out as well. So we're left with NADH, and I hope that the discussion of all the different pathways that are affected in this patient who's consumed a lot of alcohol, I hope those are clear now.
Thank you for watching MedLearner TQ Learn. If you found that helpful, please like our video, subscribe, and of course, ring the bell. And if you're really brave, be a hero and share some knowledge with a friend. Until next time.